Right, welcome everyone to another OCP Tap call. This is call number 114. Today we have Simon Kennedy. So Simon Kennedy graduated in 2015 from Carleton University with a Bachelor of Engineering Electrical focused on telecom circuits. After graduation, his first job was working at a startup, providing engineering services for Canadian nuclear labs, making custom automated testing equipment. Following that, the companies transitioned into making laser metrology products for industrial process control, largely sold into the lead acid and lithium-ion battery industry. For the last 2.5 years, Simon has been working uh, uh, on the application team in microchips, like timing and clock group, known as TCG, supporting the 1588 in advanced phase recovery algorithms. So today's talk is about PCIe time transfer. And I think with no further ado, we'll give the floor to Simon.
Ready? Yeah, like Ahmad said, we're talking about a PCIe time transfer concept today. And the first thing I wanted to get into was to talk about the underlying component that makes all of this work, and that is the differential phase lock. So this is a circuit that is commonly used to synchronize frequency and phase of a local oscillator with an incoming signal. The key components of the differential phase lock loop are the phase detector, the loop filter, and the differentiator. And for this project, the differentiator is probably the key component because that allows us to measure phase between two different signals.
Who's on cat?
Sorry, I muted it. Someone had a hot mic.
All right. So the working principle is that the phase detector can generate an error signal based on the phase difference between two input source signals. The loop filter can smooth out the error signal and generate a control signal from that difference. And the differentiator helps in accurately tracking phase changes between those two sources.
Mhm.
Differential phase lock loops these days are pretty much everywhere in digital communications. They're commonly used to synchronize phase of signals from different sources, ensuring proper timing and synchronization in communications systems. In modems, they're commonly used for demodulating phase modulated signals by tracking the phase change between two sources. They're also commonly used in frequency synthesis when you need to generate stable and precise frequencies based on phase difference between two sources. And they're also commonly used in signal processing, where phase synchronization between multiple sources is critical. They're very robust. They're closed loop systems. They're very accurate, and they can operate over a wide range of frequencies, hertz, kilohertz, megahertz, and gigahertz. So the objectives for this project were to use a 100 megahertz signal that is common to all cards on a PCIe bus. And we wanted to try and use that signal as a common reference between various PCIe cards and use that to generate a frequency that would be common to all the cards. That is aligned with a input reference. So this would increase system capacity by providing a mechanism for scaling by adding out more units. And we wanted to use existing clock synchronization hardware and software. So the general concept behind this project is that we would have an input source up at the top from primary reference clock or source. This could be a sync-E signal that is coming in from a PHY, or this could be a frequency signal from a GPS. And the idea would be to provide frequency synchronization to all of the other cards using only one card as the time transmitter, and the rest of them would just be followers. So the time transmitting board would receive that input signal from the primary reference, and it would measure the phase between the primary reference and the PCIe clock that is common to the other cards. And then we would send that phase measurement to each of the other cards, which can then be used to synchronize their outputs to that primary reference. So in general, this messaging channel between the boards, this could be anything. In our demo, we used Ethernet, but this could be any means to transmit a single number. So I was transmitting one phase measurement from board 1 to board 2. And this is expandable, so you would just need to continue transmitting that number to the other boards in the system. So when board 2 receives that phase number, board 2 would perform its own phase measurement. And then using those two phase measurements, we would overlay that phase data over PTP timestamps. So we were trying to use our PTP advanced phase recovery algorithm, and with those phase numbers overlaid on top to synchronize the receiver boards to the transmitter. This is the demo setup. This is what I had set up in the lab to test this idea. And these Azurite boards and these 1588 boards are evaluation boards for Microchip's PLLs. And the 9x9 board just serves as a source for the two boards where we can control the offset. So the common 100 megahertz clock coming out, that is to simulate the PCIe clock. And then the 125 target signal up there signifies the GNSS or the sync-E signal that we're trying to synchronize all of the other cards to. So using this setup, I was able to control the offset between the common clock, the target frequency, and I was also able to control the offset of the local oscillator of board 1 and board 2, just to make it sort of a realistic scenario as far as frequency offsets. So I was using the feature provided by that phase differentiator to measure the phase between these two, the inputs, the incoming signal and the PCIe bus. And then I used Ethernet to just send a single number, which was that phase measurement, to the second board. And then we did some calculations with that phase number to overlay the phase difference between these two boards into PTP timestamps, which we then fed into our 1588 algorithm. And that 1588 algorithm controls one of our output PLL, so it can provide phase and frequency shifts on this PLL based on the timestamps coming in. And what APR does is it tries to reduce the phase difference between the two boards based on the 1588 timestamps. So using this scheme, we were able to get a frequency lock between these two boards, and it would be pretty trivial to add additional boards to this, because it is just, all it requires is the single phase number transmitted from the leaderboard. Here's a quick rundown on all of the calculations we did. So generally, the key variables here are the phase measurement on the leaderboard, that's board 1, the phase measurement on board 2. Power up difference is the difference on the first phase measurement done. We kind of do this to normalize the phase values between the two boards. And then the transit time. This is just a constant value added to make the 1588 algorithm happy. Generally, it wouldn't understand a transit time of 0. It wouldn't really work well with the algorithm. And then the current time is just the current CPU time at the local device. So to take this phase data and overlay it onto the PTP timestamp format, we took T1 as, well, all of these values are basically current time with an offset generated by the phase difference between the boards. So T1 would be the board 1 phase. So TI is time interval error. We can just think of that as phase. So we would take the board 1 phase, subtract the power up difference, and save that as our T1 timestamp. For T2, we would take the board 2 phase and add the transit time, which was a constant. And T3 was the phase on board 2. And T4 was the phase on board 1 minus the power up difference plus the transit time. And so using this scheme, and you put those timestamps into our 1588 algorithm, and the update rate I was using was about 8 packets per second. So we're doing 8 of these measurements every second, and then passing 8 packets, sort of fake packets that we're synthesizing into the algorithm. And then the algorithm works to correct the phase by controlling this DPLL here that is in NCO mode. That is just number controlled oscillator, numerically controlled oscillator. So using that demo setup I showed on this slide, I was able to get these results. So in this case, the offset between the PCIe clock and the primary reference is 300 ppm. And this 300 ppm number comes from the PCIe standard. So that 300 ppm is a requirement on that 100 megahertz clock that is common on the PCIe bus. And then board 1 was offset by 5 ppm and board 2 was offset by 100 ppb. And these are kind of realistic numbers for OCXOs or TCXOs. And then the frequency offset between the PCIe and PRC was 300 ppm. The phase acquisition rate, yeah, this was the packet rate I was describing before. It was about 8 hertz. And on the top left here, this is the best graph. This sort of shows the time interval error between the follower board and the source signal. So you can see here it starts with a good amount of error, and then we go down, and then since the time interval error is flat here, you can tell that the two signals are frequency locked, and it just stays that way for the rest of the run. And you can see this is the frequency offset on board 2, starting uncorrected, and then our PLL starts working, and then we settle at this negative 100 ppb offset on board 2. And then here is the phase between the two boards. You can see the algorithm. So this first one is from the normalizing calculation where we subtract out that power up difference. And then after that, the first packet has the largest phase offset. And then this is the algorithm doing its work to reduce the phase offset by adjusting the frequency on the NCO PLL at the output. And that's sort of the concept in a nutshell. So this would be useful for systems with multiple PCIe cards that wanted to achieve frequency synchronization without a shared synchronization line. So basically, you just use a digital communication channel. In this case, we used Ethernet, but this could be any communication channel that would let you send a number between the cards. And then the PCIe bus, 100 megahertz signal is given. That'll always be there. And then you would need a PLL, a differential PLL, to be able to make those phase measurements, and something like a 1588 algorithm to control that PLL and adjust our final output. So that is about it. That's all I have for. Are there any questions about this?
We can start the open the floor for questions. Or is it just like a middle of the presentation, or you're done with the presentation, Simon?
That's about all the material I had.
Yeah. Okay. And also just to clarify, that confidential is something we can ignore, right?
Yes, that's just part of the slide deck. I always use my slide template.
Yeah, so let's if there's no question, like I mean, if you guys need someone to start, yeah. Tarek, you want to ask a question?
I unmuted myself. I just want to add a comment. Like by virtue of the APR algorithm that Simon talked about, it does as well time synchronization as well as PFM. Because I saw the interest was the PFM over PCIe, but the network PLL that we have here and with differential locking, we can do time as well. So you synchronize time and frequency at the same time.
Mhm. So basically, this will be, let's say, an alternative, not alternative. I mean, it will be like a complementary thing, in my opinion, for
Correct.
PTM.
Correct.
Yes.
And the issue here would be really transmitting the proprietary, like differential phase information in parallel to PCIe. And this is what we have to think about, how to transmit that information from board one to board two in order to construct those timestamps going into the software.
I mean, board one and board two are clients of that host, so the operating system
Exactly.
has
Yeah.
access. It shouldn't be a big deal, yeah.
Yes, I agree.
And then in terms of the necessary hardware, like is there anything more than like the existing thing? Like basically like the diff pair for the clock, and you have one PCIe lane minimum. There's nothing else you need. Is that correct?
Absolutely. Simon can comment on that, but there is nothing else. There is no extra hardware. No.
Yes.
No, I think you would need a relatively stable oscillator on these boards. Good oscillators would help, but no, it's just a PLL. And
Greg, do you want to add something?
Sure, I guess I'll ask questions because there's been a
Yeah.
few things that
Yeah,
were
please
kind
go
of
ahead.
glossed over here. So maybe you can comment though, what is some of the challenges though? Because with PCIe clock, especially in common clock mode, a lot of these systems are running with spread spectrum clock. And so how do you measure phase of a clock that is now being spread spectrum manipulated? How do you measure that to get a meaningful measurement between two boards? You didn't really comment on that. And the other thing is, although you say it can be done with all open hardware, your APR, I assume, is not open. And so you're not really highlighting that because it's an adaptive algorithm. And I assume that is microchip confidential and proprietary. So I assume you're not opening up how you're doing that type of filtering and things like that. So those are just some things I noticed that you didn't quite talk about. So I was just wondering if you could maybe highlight, is there advantages of maybe doing measurements instead of at the phase level, but at the frequency level between the clocks and using that to pass between the boards? Thank you.
Simon?
Yeah, I'm just thinking about that. I did not test this with spread spectrum on the PCIe bus. I was just using a 100 megahertz clock that had the same specs as the PCIe bus 100 megahertz clock. So that would be something I would need to try with spread spectrum. One moment here.
One thing, Greg, I'm just wondering again, for the frequency should not make a difference, right? Like when it's with spread spectrum, because you're looking for the differences. For the phase, you're right. Like my
Well, that's why I was highlighting that one of the limitations I see if you're doing a phase measurement as highlighted between two clocks. You're right. If they are themselves, fairly jitter-free type clocks, you're right. What you're showing here is valid and can be done. But of course, and it was commonly done, years ago in telecom, right? It was a Pluto synchronous type clocking. But the challenge with data centers and with the PCIe common clock is the whole spread spectrum clock. And so there, even if you add some sort of filtering to try to filter out the spread, then the alignment of the edges you're trying to measure, you can't guarantee they are equivalent on two different boards.
Yes.
So that's where I was saying is that's one challenge that has to still be overcome with this type of implementation. So you have to find a way to do that. So basically highlighting that you probably need complementary capabilities, either PTM or some other mechanism to try to aid in the recovery of the phase information between the two cards. So that's all I was highlighting. But the other
Yes,
one
no,
was
no,
is
fair. Fair, fair.
and then also because of that, that's where then the impact of, because you're doing a filter, that does have an impact to your overall, right? Because it
Yeah.
becomes an additional serialized filter going into the overall. So that's just some of the things I wanted to highlight. It's just they were kind of weren't discussed, and I want to make sure people understand that it's not just simple plug-in devices and go with what was proposed here. There are other challenges that need to be overcome. And like I said, by feeding it into this APR, I was a little concerned because to me that's a bit misleading, saying that this is an open architecture in terms of how to do frequency measurement passing. Sorry. Yeah.
Greg is like from the network PLL software, whether it's open or not. I mean, this is one example. There are open software.
Okay, so the APR is integrated into your PLL then. It's not, because what you're showing on the other picture, it looked like it was just something running on the board. So I assumed it was running on a processor.
Exactly. It's running on a processor. So
okay.
it's the, the known 1588 software you guys provide it for free. We have a little bit of copyright there. We have a little bit of patented core, but any other network PLL can do the job. So it's just the idea, like the piece of software that Simon did to prepare the timestamps. That's like, that can be given out. That's not a problem, and it can be associated with any network PLL. So we just used ours as an example.
Okay.
Yeah.
Cool. Question, Tarek, is this method and also to Simon, this method does not require spread spectrum, is that correct?
No.
Okay.
And I still have to research that, and that's a good idea that you mentioned it, because I'm going to see these questions at the ITSF. I'm going to research it, but I don't see any limitation there if you're measuring the phase between two boards.
Yes.
It doesn't matter the spectrum on the PCIe common clock.
Yes.
I will research it though. A very
Yeah.
good question, Greg.
So maybe a question to Greg, because Greg is very familiar with the approach that Julian has been doing. So SPED spectrum is a requirement for what Julian is doing. Is that correct? Like on the PFM?
Correct. Yeah, you have to include spread spectrum. It's a commonly used, it's commonly enabled, and it's enabled at the host, and it's
Not in the motherboards that we were dealing with. There were some there was a handful of motherboards that had SPED spectrum. A lot of them didn't, and these were like consumer grade motherboards, right?
yeah. Well, so like I said, it's the use of spread spectrum being able to be on and off is a requirement as part of the PCIe standard.
I see. Mhm.
And so a lot of the testing you have to do both because Intel requires you to test both. And there's requirements needed to be met. So that's all I'm highlighting is you can't ignore it. So I'm not arguing what was presented is
Yeah,
not
yeah,
valid.
yeah.
It's just you have to highlight there is more investigation needed to understand the impact of on the spread. Um, Looking at when you're doing a phase measurement because you're effectively trying to measure edges, but if those edges are effectively being you know
Spread.
spread, it's very difficult, right? So it means that you have to either add additional filtering to the measurement, and then of course if you have large offsets like you highlighted up to 300 ppm, then that also becomes an issue because 300 ppm translated to phase, that's about 300 microseconds per second drift between the two clocks. So either you have to make multiple measurements very quickly to try to avoid seeing that, or you're going to have that incorporated into your error, right? So which effectively is why PTM has some limitations, right? Like I know there's been a lot of discussions on PTM, and there's always been highlighted that one of its, although its concept is good, one of its limitations is if you have two free running clocks on both sides, there can be tens of nanoseconds of error over time, a variation between those two clocks, right? So that is no different in this situation. But as you highlighted, because we're trying to focus primarily on frequency, it may not be a huge impact, but it just needs to be studied and looked at.
One more thing, again, correct me if I'm wrong. I mean, from my perspective, PTM is always, let's say, device to CPU measurement. So, I mean, the device to the root complex of the CPU, which then that translates then to the TSC of the CPU. So, methods like this can be really a good, let's say, complement, if not replacement, to when you want to do device to device. Because if you want to do PTM for device to device, you basically have to use two loops, like of two devices, like device to CPU, and then figure out the computation in between. Is that correct, Greg?
Sorry, I didn't know if you're directing that to. I
Yeah,
didn't want
sorry.
to overtake this, right? It is Simon's
No, no, of
presentation.
course we have like
So
a good
you're right.
community discussing.
Like I said, the using common clock transfer is well known. As Tariq highlighted, we've all done it who are involved with timing and network timing. On the concept of, I think they even highlighted, they called it like a differential clock type recovery. It's
Hmm.
very common and it has been used in different scenarios. So I don't think what is presented is invalid. It's an approach that we want to look at because as you highlighted, one of the difficulties with data centers is there's no way of nicely getting clock information from one board to another, one peripheral board to another, or NIC board. So
Yeah.
so that's the challenge. We're trying to find ways to do it. So this presentation is highlighting that a method that is very useful and can be used, but it does have some challenges that were not seen in traditional ways it was used in the past in telecom. We didn't have concepts of spread in telecom, right? So
Yes.
you didn't have to worry about it. So But there's other issues with telecom with differential clocks, right? The sources may be traceable to each other, but the phase relationships could be different. But as Tariq highlighted, when all we're focused here is the frequency component is what we're trying to recover. Because by recovering frequency component, you stabilize the boards commonly. So then other PTM and other things can help aid and get even more precision in the phase and time relationship between those boards as well, without a physical clock. So that it is a very advantaged technology that needs to be looked at.
It
Thank you.
does need special phase measurement tools when you have a spectrum clock, definitely. So let's say,
Oh, you mean that device, the third-party device that sits on the right side, right?
correct,
Yeah.
And in our meetings with you guys, I believe we said let's make sure it's turned off spectrum right now and
Yes.
focus on the frequency. And given that environment, we managed to measure the phase, and we managed to also synchronize the phase. But a great point. We have to investigate that and look into it.
Yeah.
Yeah.
Maybe I can ask a customer side of a question. So let's say I want to go, like, again, very specific again. It's like more a question to application engineers. So I have, let's say, in my system, say, multiple GPUs, and I have a single network, like a front end. I mean, I have also back ends. Let's say I have a front end network that from there I have access to, let's say, all the way to my time card and grandmasters and all of this. So now time is brought to that NIC. And then from there, I'm also just in the background running PTM to have the CPU for that system uh, getting, like, the sync between the NIC and the TSC of the CPU. So now, what do I need to make basically this architecture to have precise frequency, like synchronization, basically, between, like basically between the GPUs and the NIC. So then I assure when I have multiple of these, let's say, setups together in a network connected together, like all the GPUs then in this, like, the composing GPUs of all these systems also align in terms of frequency. So what is the minimum needed? Like, do I need also this extra, let's say, I don't know, it's like perhaps like a 10 megahertz, or in this case it's like 125 megahertz that they have to go to some comparison, like for comparison to a comparator, and then so that, like, there is additionally like some more things required other than just the PCIe connection. Is that correct, Simon?
Yep, you would need the PLL with
Mm-hmm.
phase measurement capabilities, and
Mm-hmm.
you need at least one leader card with the follower cards complementing it, and the 1588 algorithm. And I think that's about it. Well, I guess on the follower card, you'd probably want as stable as an oscillator as you can afford. But I have not tested the extremes on that, how tolerant the system is to huge offsets on the local oscillators of the other cards.
Mm-hmm. Maybe we should also look into our time card and see what do we need to add, let's say, to the time card to be to provide, let's say, one side of like this equation, and then basically we look into what's needed to add that to the NIC, and then what's needed to add it to, let's say, devices. Would this only work with that 125 megahertz, like 8 nanosecond, I'm assuming, or you can also live with 10 megahertz because that's something that's standard on our devices, let's say.
Yeah, no, we only used 125 as an example. That could be any frequency.
Okay.
I don't believe the 125 is a limitation, Simon.
Yeah, it could be any frequency.
It could be anything.
Yeah, no, I just use that because that's a common syncy.
I think the issue here, if I can summarize, like Ahmed, if you can get some information from the customer, when would they turn on? Is their application does their application require, let's say, spectrum to reduce EMI for like board density, like fan out of the clocks and all of that stuff? They use the spectrum for that. Do they need it to turn it on? And if it is, we have to study and see the limitations. I assume we're going to see levels of noise on the phase, on the recovered phase. It's not
Yeah.
going to be as clean as shown in the picture. You will see some levels of noise there. And now, how noisy, what type of filtering, that can be controlled through the network PLL software itself by the filter choice, or it might need an extra added filter to the software, which I doubt. I think the PLL itself, you can program it to control that type of noise, that level of noise.
I
So
am assuming, I don't know, and maybe Greg has answer to that. So right now, you have from every device going to, let's say, in this case is a counter. You have basically a sample from the frequency. Maybe from every device also you collect, let's say, a phase, like a PPS. And now if you have the phase, like a way to compare the phase, then you can somehow, like, tackle the problem with spread spectrum. Spread spectrum is like a must for us when, especially we have like higher lines for like, or let's say our PCI here and other things. Again, it's to reduce EMI, like otherwise you cannot even, like, that's basically implementations were not working. And then spread spectrum was introduced and okay, we stretched a little bit more things working. So Greg, what do you think?
All right. Yeah, like you're right. Like that's the thing is we have to make sure we consider we can't just make statements like, well, we'll just assume spread won't be available or not needed, you know. But as you highlighted, things get added over time, so the whole concept of spread was added to address an issue. But who's to say once you have phase and time synchronization between your cards, it may eliminate the need for spread because you have different ways that you could try to maybe mitigate some things that we're seeing, right? So that's the thing. You don't know what's going to
Yeah.
happen once we get this going and everything's working. You're right. But I think what we have to focus on is we have to assume, that there's a, PCI SIG requirement we got to follow to be compliant to PCIe clocking. And so those have to be a must, right? And so because of that, we have to make sure we test both scenarios of non-spread and spread. But you're right. Over time, we may learn, hey, we don't need spread anymore because this actually eliminated the original issue, right? We have different ways to now mitigate what we were seeing before.
Yes.
So I agree with that statement. Yes.
No. So, a question for you, Simon. The the element that you have on the right side, let's say here, the counter. So that, I mean, that's I'm assuming is like an off-the-shelf like counter. You're measuring basically the difference between frequencies. That one, if I mean that needs to be part of the system. What is the minimum for that you can do? Can you just use, let's say, a mixer and do things in frequency domain, and then you look for like a mixer with a low pass, and then you look at like the component that you get between the two. Is that correct?
the counter here, it was just to measure the output. It's not really part of the system here.
It's not part of the loop?
No, this is just to measure the output to generate the graphs at the
Oh,
end.
okay. So this was just
That's
to validate
yeah,
this implementation.
that was where this plot on the top right was coming
Yes.
from that counter.
Sorry.
Nope.
That might be like being in a call middle of the night.
Yeah, so that was just measuring my outputs
Okay.
and making sure that I got frequency lock.
All right. Anyone else from the audience? Sorry, we got like we went deep into some discussions with some background that we had. Hisham, go ahead.
Yeah. Simon, you mentioned a conference, ITSM, or I missed it. Which conference is this?
I believe Tarek is presenting it at ITSF.
It's
Yeah,
ITSM.
I mentioned it, ITSF next month, November 3rd to 7th, or 4th to 7th in Seville.
Let me look it up.
ITSF 2024. It's the equivalent of WSTS we have in North America, the timing forum in Europe.
Posted a link for you there. Hisham.
Yeah, thanks, Greg. That's
All right. Any more questions from the audience? All right. Hearing none, we can probably give you guys back about 15 minutes and we'll see everyone in 2 weeks. All right. Thank you,
Thank you.
everyone.
Thanks, everybody.
Thank you.
Bye.